All right. So we're going to get into the term electronegativity. Now, this is a lesson that isn't covered in your book. So this is all you're going to see about it for now. Electronegativity is a really fancy word, and I really wish there were a better word for it, because this is not electrostatics. Electronegativity, is not the same thing as electrostatics, although it takes a lot of the concepts that you know about electrostatics and puts it there. So the first thing you need to know if we're going to talk about electronegativity is what's called the effective nuclear charge. And in this case, Z means the charge of the nucleus. And this means, unsurprisingly, effective. So I don't know why they made Z equal to the charge of the nucleus, but they did. So what we learn is that valence electrons are shielded from the nucleus by core electrons. So really, it's like those valence electrons are farther away from the nucleus, so they can't feel the pull of the nucleus as strongly. And you have these negative charges that are sort of, stealing all that positive pull. So each core electron effectively cancels the charge of one proton. And the effective nuclear charge tells us the charge the valence electrons feel attracting them to the nucleus. So that's why it's called the effective nuclear charge. It cancels out all the core electrons, and that's just what those valence electrons actually feel. So as you go from top to bottom in the periodic table, so this is in a group. So this is a group. The effective nuclear charge stays the same. Right? Because every time you go down one row, you're adding another energy level on. So that addition of the energy level makes all those extra electrons core electrons now, and it cancels out the charge of the increased number of protons. So the effective nuclear charge, the effective pull that the electrons feel from the nucleus stays the same, except for the fact that the distance from the nucleus increases because your atoms are getting bigger. Now, Coulomb's law says if the charge stays the same, remember Coulomb's law is that the charge is in the numerator, the distance is in the denominator. So if the distance increases, well, what does that mean about the force that it feels? So think about this for a second. The distance between them increases. Your denominator gets bigger. What happens to the force? So yeah, the force goes down, and which means the attraction is weaker. So that what we're saying here really is as you go down a group in the periodic table, those valence electrons aren't getting held onto as tightly because they're still essentially feeling the same pull from the protons in the nucleus, but it's further away, so that pull gets sort of deadened a little bit, right? So another way we could say that is francium, Fr, is weaker than cesium, is weaker than rubidium, is weaker than potassium, etc. So potassium can hold on to its valence electrons more strongly than francium can, because the valence electrons in francium are further away. But now as you go from left to right in the periodic table, the effective nuclear charge increases by 1. So as by 1 each time. So if we look at the third row, the third period in the periodic table, sodium, which has 11 protons, goes to the next one is magnesium, which has 12. Well, they still have the same number of energy levels, the same number of core electrons, but every time I'm adding a proton now, as long as I stay in the same energy level, the same period, my effective nuclear charge increases. So that means the force felt by the electrons will stay the same because the distance is about the same. So if the charge increases and the distance stays the same, well, the attraction gets stronger. Now, what I noted with the distance from the nucleus, I said it's approximately the same. What actually happens, which is really cool, is that as you move from left to right in the periodic table, you get more protons in the nucleus and it pulls tighter. So even though you're adding protons and electrons, your atoms get smaller as you move from left to right. So sodium is actually the biggest atom in the third period, and argon is the smallest, even though argon has a higher atomic number. That's not something you need to know for this class, but it is something that you'll have to know if you take college chemistry or AP chemistry. But then as you go from argon to potassium, you're adding another energy level, so potassium is much bigger than argon. Okay, so what is electronegativity? We'll talk about this a bunch when we talk about bonding in molecules later in the year, but really electronegativity it's a rough measurement of how strongly an atom attracts electrons in a chemical bond. And it goes a long way to describing the properties of metals and nonmetals. You can actually look on your periodic table too and see that you have numbers corresponding to electronegativity values. So if this is your periodic table, well, your weakest attraction is down in the bottom left, and your strongest attraction is on the top right. And a way I like to remember this, which is silly and I feel sort of badly about it, francium, maybe France is, in recent generations been a little weaker. So francium, France is the weakest. Whereas we live in the northeast of the country, the northeast of the periodic table is the strongest in terms of electronegativity. So the question from the day is, what does the arrangement of electrons tell us about how strongly the nucleus attracts them? And what we learned was electronegativity measures how strongly the nucleus attracts valence electrons. And it increases toward the top right of the periodic table. And we don't really count the electronegativity of noble gases because they don't make bonds. So electronegativity is higher in the top right. Francium has the most electronegativity of any element. And it is lower in the bottom left, francium being the weakest.